So we wrote the Rayleigh-Schwinger equation in curved space-time, basically covariantizing that on flat space-time, replacing ordinary derivative by covariant ones. But then what we need to require in order for psi, the gravitational field, as a massless field to be consistently defined on a curved space-time as well, is that we can decouple its longitudinal modes, which are physical. We have to require this. So we have to associate with it a local invariance, gauge invariance in quotes of this form here, defined by, parameterized by a spin 1/2 parameter, local spin 1/2 parameter, just as we had in on flat space-time. Okay, this is needed for the description, or consistent description of the gravitational as a massless field. However, as you can see, in curved space-time, the Rayleigh-Schwinger equation is no longer invariant because the commutation of two covariant derivatives is non-zero. They don't commute any longer. Okay? So this is a problem. So Rayleigh-Schwinger alone does not describe consistently a massless gravitational field. However, notice that this gauge transformation, which is associated with the gravitational field for its consistency, okay, is nothing but a local supersymmetry transformation. It's parameterized by a local spin 1/2 parameter. So it is a local spin 1/2 supersymmetry transformation. So whenever you have a massless gravitational field, you have a local supersymmetry. And vice versa, whenever you have a local supersymmetry, you must have a local a massless gravitational field, which is the corresponding gauge boson. Okay? So there's a one-to-one correspondence. Supersymmetry is really needed for the gravitational field to be consistently defined on a curved spacetime. Now, therefore, as I said, a consistent definition of the gravitational field on a curved spacetime requires invariance under local supersymmetry. Now, as we've seen, Rayleigh-Schwinger alone in curved spacetime is not but a theory combining the gravitino and the gravity field, that is a theory, gravitational field in which gravity is coupled to gravitino, is invariant. So if we couple gravitino to Rayleigh-Schwinger field to Einstein gravity, as we shall see in a moment, then the theory is invariant under supersymmetry, and therefore it can describe consistently a massless spin 1/2, a spin 3/2, a massless gravity, because it is invariant under this supersymmetry transformation, that is the corresponding gauge transformation. Now, it is convenient, before proceeding in this direction, it is convenient to write down an action density for the gravitational field. You can easily verify, prove this, that starting from this Lagrangian density and deriving with respect to the gravitational field, you end up with this Rayleigh-Schwinger equation. That's easy. You verify the gravitational field, you get two terms, but these two terms are using properties of the gamma matrices. Okay, so you write them in terms of a single term, okay, in which the variation of the gravitational is in the leftmost position. Then you drop it, and then you get your Rayleigh-Schwinger equation. So I suggest you to prove this. Yeah.
In the previous slide, the last time, the gamma is 3 indices.
Yeah. Now there is a 3 index term. You see, this gamma has 3 indices. These two are equivalent because of a property of gamma matrices that I'm going to write down. You can easily prove that with some gamma matrix algebra. Gamma 5 for me is I times gamma 0, gamma 1, gamma 2, gamma 3. Okay? And that is equal to, in the basis I'm using, minus 1, 1. I'm using a basis which is the Bayer basis, the Bayer representation. So gamma phi, you can easily deduce from this as gamma phi times gamma A, B, C, or nu rho, is equal to square root of G. This is square root of the determinant of the matrix times epsilon nu rho sigma gamma sigma. Check this. Now if you use this property, you have to use this property here. I use here E, but what is E for me? E is the square root of the absolute value of the determinant of the matrix. This is my definition of E. This E. Okay.
I think maybe was the question, what's the definition of gamma mu rho? Like then the symmetrization.
Oh, I'm sorry. Sorry. Yes. Gamma mu rho. Yeah. This is the 3 times antisymmetric. It's gamma mu, gamma rho, antisymmetrized. So this is equal to 1/6 times gamma mu, gamma rho. Yeah, sorry. Plus all permutations with plus or minus, depends on the sign of the permutation, right? So this is gamma mu. When I write gamma mu here, this is 1/2 gamma mu minus gamma mu. Yeah, this is the usual. Okay, so we can. It is useful to write the Lagrangian density in terms of a Lagrangian form. So to use the exterior form notation because it's easier to. It makes invariance under diffeomorphism manifest, and it's easier to vary with respect to various fields using the exterior form notations. Okay, you suppress a lot of indices. You make your life simpler with the exterior forms. You see, so it's a more compact form. You write the Lagrangian I've just written in the previous slide. Okay, times the d4x. Okay, the volume element of Minkowski space, where it's not Minkowski space, of your space-time, d4x, as a 4. The square root of the determinant of the matrix, which has to be is in the definition of L4 LS RS. Okay, this is in the definition there. So this is the density, Lagrangian density. So the 4 form, a later speaker, Lagrangian density, has this expression here. You can verify this. I suggest you to check this. You have to use these properties. You see, and in particular, this relation between dx mu, h dx mu, h dx rho, h dx sigma, with the volume element. There is an epsilon symbol there. Okay, and our convention for the epsilon symbol is simply that. The epsilon symbol is always a constant, plus or minus 1. It's different from 0 when all indices are different and it's totally antisymmetric. And our convention is that epsilon 0, 1, 2, 3 is equal to minus epsilon 0, 1, 2, 3 and is equal to plus 1. From this you deduce the expression of all the others. Okay? So try to do this exercise. You clearly see that BA, wedge BB, wedge BC, wedge BD is nothing but minus the square root of the determinant of the matrix times epsilon symbol times d4x using the notation above. Okay? In case you have any problem, you can work it out together. Okay? since we're going to couple it to gravity, it is useful to write the Einstein-Hilbert term in the same way, namely in the exterior form notation. So we write a four-form Lagrangian density. The Lagrangian density of the Einstein-Hilbert the Lagrangian is this one. With K is defined, I hope I defined it somewhere here, no. Kappa is square root of 8 pi Newton's constant. Okay. We'll often set it to 1 in our calculation, but here I'll keep it explicit. Okay, this is the Einstein-Hilbert Lagrangian density. As a fourth form, I suggest you to prove that it is written in this form. So it's a good exercise to check that this and these are related. This is the definition of the Riemann tensor, as I gave earlier. And this is the Ricci scalar, when you contract all indices. Okay? Okay, now we want to put these two regions together. Spin 3/2 field, spin 2 field. And prove that the combination is invariant under supersymmetry. So, pure n equal 1 equal 4 supergravity. We put these two terms together. Okay? We get a single Lagrangian density 4 form, which has this form here. Okay. There is a bracket. There is a bracket there, but it doesn't show. Okay. So we use the first order formalism, which is the most convenient one, which was the one in which supergravity was derived by Bezel and Tonino in 1976. So what does it mean? Let me consider the spin connection omega to be an independent field. It is not an independent field. We know it's a composite connection because the condition that on the torsion, that the torsion is not dynamical. This is one of the assumptions that we're using here. The condition that the torsion is not dynamical fixes omega in terms of the field by and also, as we shall see, of the gravitino field. Here we are going to have another condition, a torsion condition, but which fixes omega in terms of all the other fields. Okay, but let's not update it now. Okay. So we consider spin connection as an independent connection. So we have as an independent field. So we have three fields: omega, psi, v. Gravity, gravitino, omega. We vary with respect to them. We first vary with respect to omega and derive the equation of motion for omega. If you vary with respect to omega, what is omega? Omega is in R, is RAB. It's much easier to use the exterior form notation. And then vary omega by an infinitesimal quantity, delta omega AB. And then use this property that you can easily verify that the variation, the infinitesimal variation of the Riemann curvature, RAB is the Riemann curvature, is a two-fold. Recall what the convention that were given in the previous slide. RAB is not the Ricci scalar, the Ricci tensor, but is a two-fold, which is R mu AB dx wedge dx divided by 2. Okay? Now, if you vary this, you get variation, the covariant derivative of the variation of omega. Then you integrate by parts, and you find this way. When you integrate by part the Einstein-Hilbert term, the derivative hits the field line. Here it is. Okay? Then you have the omega in the covariant derivative of psi in the second term. Remember, the covariant derivative of psi has an omega inside. So you have two terms. And you can easily verify that. Then, okay, that this equation can be written in this way. Now this condition can be interpreted as that the super torsion defined by this combination vanishes. This combination is called the super torsion. This is a supersymmetric torsion. Okay? But in terms of the torsion, this is telling you that the torsion is different from zero. This is typical in supergravity. In supergravity theories, there is torsion. The connection is generally this torsion. The reason is that how do we define torsion? The covariant derivative. What is this? This is d nu a. I'm not anti-symmetrizing here. So minus gamma g nu rho v rho a plus omega a b nu v b nu. This is the definition of T. Okay. This is recall that this is the Levi-Civita. This is symmetric. Levi-Civita symbol. This is symmetric. There's no torsion here. Now this is equal to twice. No, sorry. Yeah, this is equal to what is called the contortion. The contortion tensor. Okay? Whatever you find on the right hand side is the contortion tensor. If you anti-symmetrize, this goes away because this is symmetric. So if you anti-symmetrize, so you compute this guy. Now indices nu are anti-symmetrized. This drops out, and you get dA plus omega AB wedge dB, which is this term written in form notation. This written in form notation. This is equal to this anti-symmetrized, but this is the torsion. Okay, so whatever you find on the right hand side, this is the torsion. This equation is telling you that this is equal to I over 2 psi bar gamma A psi. So you have torsion. Of course, how do you solve this equation? This equation can be solved in omega. Okay, so you solve this equation by writing omega as a function of the field by left side. There is the details of how you solve this equation, but straightforward, you can find on the lecture notes. I can show you later if you want. Okay. Okay. So to derive this equation, I'm using these properties of the field of the gravitational field. Okay. Recall that the gravitational field is a 1/4, as written here. It's described as a 1/4. This means that its space-time index is contracted with dx. Psi is psi mu alpha dx mu. So I'm suppressing alpha, and mu is contracted with dx mu. So it's a 1/4. It's a 1/4 field. This is a Grassmann variable. This is a Grassmann variable. Okay, this means that they anti-commute. But since dx anti-commute, this is a commuting variable. So psi alpha, psi beta is equal to psi beta, psi alpha, because we have two minus signs. One when we swap the components, the other when we swap the dx mu. So it's a commuting variable. Then we have these properties, okay? And using this you can prove that you get this torsion equation. Okay, so you do consider omega as an independent field, you work out the corresponding equation, and the corresponding equation fixes omega in terms of V and psi. In the second order formalism, what you would do, you start from this guy, this equation, you solve it, you plug it, the solution, omega, inside the Lagrangian, and then you work out the equation for motion for the arms. So you start from considering omega not as an independent variable in the second order formalism, but already as a function of psi at B. Okay.
Some people like the 1.5 order.
1/2, yeah. Now I'm coming to that.
Okay, good.
Yeah. Now I'm coming to that. Now the solution is a function of P and psi, but in the second order formalism it's even more complicated because you start from a torsionless omega, and then you have to work out also the higher order Fermion terms. As I'm going to show here, you don't need that because all the higher order Fermion terms, the order 4 Fermion terms in the Lagrangian, which you need, always need, they can be incorporated in the definition of omega. So the action does not contain them. If you choose omega, it will be a torsion-proof connection. So you can reabsorb all these terms in a redefinition of omega. This is typical of pure N equal to 1. In generic supergravity, this is not the case. You cannot reabsorb the order 4 terms in the fermions, which are the most complicated ones, in a redefinition of omega. But in this case, you can. And things are much simpler. Okay, so you can split omega into a torsionless one, solution of dV equals 0, plus something else which depends on psi, so on torsion. Okay, you can always do that. Okay, now what I suggest you to do is to check that this equation, this action is invariant under local supersymmetry. This is the supersymmetry translation that we want to demand, so the supersymmetry invariance that we want to demand, okay, for a consistent definition of the 13. Okay, and check that everything is consistent provided V, the feedback, is transformed accordingly, according to that law, okay, as this transformation property. Okay, how do you prove this? First of all, why do we need K? Before I didn't write K, kappa. I didn't write kappa. Why do we need kappa? Well, we need kappa because let's talk about dimensions. Epsilon as dimension of length to the 1/2. It's half a length. Because epsilon bar gamma A epsilon, 1, 2, is a length. So it has to be. Now, from the Ravita-Schwinger field itself is length to the -3/2. This is the physical dimension of psi. So this means that psi mu dx mu. You multiply times the length, dx mu is the length. This is L to the -1/2. Okay? So this means that if we want to write delta psi nu as d mu epsilon, okay, like this would be inconsistent dimensionally because this is length to the 1/2, this is length -1, this is length to the -3/2. So it's not okay, not good. I have to multiply times 1 over kappa, length -1, because kappa is the dimension of a length. So you need that in order for the dimensions to come well. So what you do, you vary the action with respect to the various fields. Okay. Now you can do this in the second order formalism, in the first order formalism. In the first order formalism, how would you do that? Well, you would have to work out the supersymmetry variation of all the three fields which are independent in the first order formalism. That is V, psi, and omega independently. Now there is another formula which is called 1.5 order formula, which is a shortcut. Well, it's a trick, but it's a useful trick. So you vary the Lagrangian with respect to all the three fields as if they were independent. But then after you did this variation, okay, after performing the variation, you replace omega AB by its solution, the solution of its equation. Okay? If you do that, you see that the first variation cancels, because the first variation is proportional to the variation of the action with respect to omega, but this is the equation of motion of omega. You have solved it. If you plug in the solution to the equation of motion, this is zero. So you don't have to bother about the varying, devising a supersymmetric transformation for the connection. You don't have to bother about the connection. Just vary S with respect to psi D. Okay? And use for the connection the solution of the supertorsion equation. Okay? So this is something in between the second order formulas and the first order formulas. So you do that, and I suggest you to perform this calculation and check that it is invariant. If you want, we can work it out later together. Okay, it's not so difficult. It's important to use certain relations which allow you to write products of psi in equivalent ways. These are called fields identities. They are, well, I give you the main fields identities here that you can use. You can find in the lecture notes. The main fields identity is one involving the product of two psi's. If I write psi bar, what is this? This is a matrix which has two indices, alpha and beta. And the first identity is telling you that this, which is a 4 times 4 matrix, can be expanded in gamma matrices. So this can be written as 1/4 times psi bar gamma A psi. This is a number times gamma A. This is a matrix. Alpha beta minus 1/8 psi bar gamma A psi. Okay, gamma A. You see, we are expanding in matrices, and these are the only two terms that you can use. Right? Then there is another equation which is important, identity which is important. Psi times psi bar gamma A1 AK psi equals 0. That's another one. Okay, use these properties. Okay, then you can prove the invariance of the action. This is very useful, instructive calculation. Now, you see, in this action, apparently there are no 4 fermion terms with order 4 in the fermion fields. However, they come out if you write the connection as a torsionless connection, depending only on B, plus all the rest. The rest will depend on torsion, and depends on psi. Now, if you write all covariant derivatives in terms of covariant derivative with respect to this first omega circle, the torsionless one, then the second term will produce order 4 fermion terms. Okay, and the equation, the Lagrangian becomes ugly, of course. Okay. So, but in general, 4 fermion terms are needed for the construction of a supersymmetric, locally supersymmetric action. Okay, are there questions? Now let's briefly discuss a first variation, a simple variant, the simplest variant of the pure n=1 4-dimensional supergravity, which was constructed by Paul Townsend in 1977, okay, just 1 year after. And it amounts to adding a cosmological term, that is, you see, this term here, proportional to the volume element. This is a cosmological constant. So adding to pure n=1 = 4, a cosmological constant. Now, what's the advantage with this? Well, first of all, the pure n equal 1 equal 4 supergravity has just one vacuum, which is the Minkowski vacuum. Okay? This actually now is a non-trivial vacuum, which has a cosmological constant. As we shall see, it's going to be an anti-de Sitter vacuum. Okay? So somehow it's more interesting. Paul Townsend proved that if you want to add a cosmological constant, you have also to add other things. Otherwise, symmetry will not be, the action will not be supersymmetric. Particularly, you're going to add, you have to add this other term, okay, which is quadratic inside, as this form here. As we shall see, this is a master for the gravity. And you have to add also a term here in the supersymmetry variation law of the gravitational field. They all depend on some parameters I call beta, sigma, alpha. Okay? If you write down the action of this form with the variations of this form, you can prove that the action is invariant. It's invariant under these local supersymmetry transformations, provided the parameters are related in this way. And in particular, provided beta is minus 3 lambda squared. Lambda is a real number, so beta has to be negative. So you cannot construct you cannot put any cosmological term, any cosmological constant. You cannot put any cosmological constant here. The cosmological constant has to be negative. Okay? This is strictly related to the fact that only anti-de Sitter vacuum, besides Minkowski vacuum, can be supersymmetric. De Sitter vacuum can never be supersymmetric. I will give another proof of this later, but this is simplest. This is the simplest. You work out the calculations, you prove the invariance of the action, and you see that beta has to be negative. Now, to prove the invariance, okay, you need to use the fierce identities. It's useful to use again the 1.5 order formalism, okay, using the fact that the equation for omega is the same as before, because the new terms don't contain omega, so the equation of motion for omega is the same as before, and it's telling you that you have a torsion, depending which is bilinear inside. You solve it just as you did before, and then you use the second order formulas. You vary the action as if the three fields were independent, and after varying, you plug in the solution of this equation. Okay? In case you have any problem in solving these exercises, you just ask. Okay? We can work them out together. Okay. So you plug in the solution to the condition that you find on the parameters, so that you write the parameters in terms of the single parameter lambda as Townsend did, okay? And we notice some general features of this action. First of all, you have a cosmological constant, which is negative. The second term in the Lagrangian, you see that is a master. Is a master, is quadratic inside, is a master for the gravitino field, and the gravitino mass is lambda. Now, this does not mean that the gravitino field is massive, because this mass that you see here, which is equal to lambda, is the Poincaré mass. The mass term that you would write if the equation of motion were written in a flat spacetime. However, as I will show, the vacuum is not flat spacetime. It's anti-de Sitter spacetime. Okay? And masses of the fermion fields in anti-de Sitter are shifted with respect to the masses in flat spacetime, okay, by a term depending on the cosmological constant. So that, although it seems that the gravitino is massive from the Poincaré point of view, but in anti-de Sitter it is massless. This is precisely the value that the gravitino mass must have in Poincaré in order to be massless in anti-de Sitter. And this is an additional term you need to add to the variation, supersymmetry variation of the gravity of fluid. Why is this example useful to us? Because this is a kind of prototype of a gauge supergravity. It's not a gauge supergravity because there's no internal gauge symmetry. However, you see from here some features that we will encounter when dealing with the gauge supergravities. First of all, in order to add a scalar potential, here there's no scalars, so the scalar potential is theta, it's a cosmological constant. So in order to add a cosmological constant, okay, you need to add a Fermi mass term and an additional term in the supersymmetry transformation property of the fermion fields, which we will call fermion shifts. Okay? This is going to be true also for gauge supergravities. In gauge supergravities, in order to introduce a scalar potential, and this is implied by the gauging procedure, you also have to introduce mass terms for the fermion fields and additional terms in the supersymmetry transformation of the fermion fields, the fermion shifts. Okay? Precisely as in this very simple model. Moreover, there is a relation between the cosmological constant and the coefficient of this fermion shift. This precise relation we will encounter in a more general setting as the so-called potential world identity. Okay? Relating the scalar potential to the fermion shift in a more general setting of gauge supergravity. Okay? So let us remember this very simple example. Let's consider the vacuum solution. What do we mean by vacuum? What is the vacuum? By vacuum solution of a supergravity theory, we mean maximally symmetric spacetime. Maximally symmetric spacetime cannot have fermion fields on it, because fermions would break Lorentz invariance. Maximally symmetric means that the Lorentz group has to be anisometry. Okay? If there is a depth of a fermion field, that would break Lorentz. Okay? So Lorentz fermion fields, they have to be zero in the vacuum solution. So the vacuum solution is a bosonic background. All fermions are zero. All vectors are zero because a vector would break Lorentz invariance, okay, of the solution. So Lorentz group must be a symmetry of the solution of space-time. Okay. And moreover, if there are scalar fields, they have to be constant, because the gradient of a scalar field would break Lorentz invariance. Okay? So scalar fields, if they exist, they can be non-zero, but they have to be constant. In this case, we set psi to zero, the Einstein equation, you can easily show that meets this solution. For the Ricci, this is the Ricci tensor. This is the Ricci tensor. Okay? But this is the anti-de Sitter space. This is the Ricci tensor of an anti-de Sitter space, which can be described in a five-dimensional flat spacetime as this hyperpoloid. You can easily show anti-de Sitter space is the solution to this equation. It's a locus of points satisfying this equation in a five-dimensional flat space, okay, with a matrix of this, with these signatures, 2 pluses and 3 minuses. If you write it like this, you immediately see what the isometry group is. It's SO 2,3 anti-de Sitter. Okay, and L. So this is a kind of big rotation of a sphere, a big rotated sphere, if you want. Okay, of radius L, and our L is 1 over lambda. L is called the anti-de Sitter radius. So this solution has a vacuum which is anti-de Sitter. And this vacuum is supersymmetric, so it preserves all supersymmetries. Okay? Are you familiar with this description of anti-de Sitter space? Okay. There are 3 kinds of vacua, maximally symmetric backgrounds you can have, depending on the cosmological constant. You can have either de Sitter with positive cosmological constant, Minkowski, or anti-de Sitter. In this case, you have anti-de Sitter. For lambda going to 0, you retrieve any pure and equal bond equal force. And if you set lambda equals 0, you get flat Minkowski. Okay, so this is the link in which we theory. Okay.
So is there a statement, we define the vacuum as the maximum symmetric
Yeah.
solution? I guess that's also the lowest energy, I mean, some definition of energy in gravitational theory, whatever.
Yes.
Solution. So these concepts correspond, right?
These concepts correspond. You can show that you can define an energy, and that all energies of all solutions to this theory are above the lowest energy, which is the one associated with the vacuum. This was shown by Gibbons and Hall, if I'm not wrong. They extended the positivity theorem proven by Witten in 1981. They extended to Anke de Sitter. And they proved that this theory, Anke de Sitter, is the lowest energy problem. Energy is it defines a lower bound for the energy.
But does this proof require supersymmetry?
Sorry?
Does it require supersymmetry? So what I mean is, if you take general GR,
yes,
does the same statement apply that the lowest energy solution would be maximally symmetric?
No, I mean, to prove this, you need asymptotic killing spinors. These are used for the proof. The existence of asymptotic killing spinors so, for instance, you find models with Anke de Sitter vacua which are unstable. So, but these are non-supersymmetric.
Yeah.
But if you have a supersymmetric Anke de Sitter vacuum, that's stable for sure, because you have the ingredients that you need to prove the possibility theorem, that is local asymptotic killing spinors. So there are few examples of non-supersymmetric, very few examples of non-supersymmetric perturbatively stable Anke de Sitter vacuum. Most of them are unstable. So this means that fluctuations of fields, they are tachyonic. So they destabilize the vacuum. Okay. Is this clear so far? Okay, so supergravity is also, so far we focused on 4 dimensions, but we can define supergravity theories in higher dimensions up to 11, no more than 11 dimensions, okay? For instance, in 10 dimensions, we have 10-dimensional supergravities, and these have the interesting interpretation as describing the low energy limit of superstring theories. Superstring theories are naturally, by consistency, defined in 10 dimensions. Okay, you have a number of them. Okay, and their low energy description is captured by a 10-dimensional supergravity theory. But you have also an 11-dimensional supergravity theory. That is a unique supergravity theory you can write in 11 dimensions. There's just one 11-dimensional supergravity. It has 32 supercharges. By supercharges, I mean conserved conserved supersymmetries, okay, supersymmetry components. So this means that the most general supersymmetry parameters contains 32 independent functions, okay? So 32 supercharges, so there's 32 conserved supersymmetries. Now, this 11-dimensional supergravity was constructed in 1978 by Kremer, Julia and Scherk. Okay? And it is conjectured to describe the low energy limit of a microscopic theory, whose definition is so far unknown, the so-called M theory. So while we have a definition, microscopic definition of superstring theory in terms of vibrating strings, okay, vibration modes of strings, we don't have the description of the microscopic degrees of freedom of this conjectured M theory. We only know that it lives in 11 dimensions. We only know that its low energy limit is captured by the low energy, by the unique 11-dimensional supergravity. Okay, but we don't know what are the microscopic objects. Okay, so the ultraviolet description of M theory is unknown. M theory was conjectured in the 90s by Witten, okay, as a missing ingredient needed to complete a duality picture, okay, of string theories. So it's useful to have this picture in mind. Supergravity, when it describes, when it's related to as a low energy limit of superstring theory, describes the macroscopic description. It provides the macroscopic description, you see, of those microscopic degrees of freedom which are described by superstring theory or M theory. Okay, very much as thermodynamics provides large-scale description, okay, of molecular models, okay, which are described from a microscopic point of view by, for instance, kinetic theory of gases and so on. Okay, so there is this interesting, if you want, analogy to bear in mind when working with supergravity. Now, supergravity theories in any dimensions are not always associated with string theories, or do not always describe low energy limit of superstring theories. Okay, but when they do, I mean, this picture holds. And when they do, supergravity provides a valuable approach for studying properties of superstring or M theories, like vacuum and the dynamics of modes around this vacuum. Okay, the dynamics of fields around. So, are there any questions? Yes.
Is there a D equals 12 theory with signature 10,2?
Sorry?
Is there a D equals 12 theory with signature 10,2?
10,2.
Yeah.
There could be, but a theory like this has been constructed recently by Leonardo Castellani. He wrote down a gravity theory in 12 dimensions with signature 10,2. You can, because the spinorial degrees of freedom, you can write a Majorana Weil spinors, so you can in principle. This work, Leonardo Castellani did some constructed gravity theory, consistent gravity theory. Now, whether this describes any F theory, I don't think so. It's totally unclear. It's totally unclear. But it would be nice, I mean, to have a supergravity description of this kind. Yeah, the only supergravity I know in 12 dimensions was this work, constructed in this work. It was constructed recently, a few years ago.
And presume it's unique. Is it unique?
Yes.
So, I mean, one would assume it's related to a theory in some way.
Yeah. Or somehow, yes. One is tempted to
just based on uniqueness arguments.
Yes.
I would agree.
I was wondering, so it's important for this signature change, so that the signature is implemented, that you still have the appropriate signature. So you can't go higher by including more time directions, higher dimensions.
In principle, but changing you could. The important thing is that the number of spatial direction minus the number of time direction has to be a multiple of 8.
Has to be?
A multiple of 8.
Oh.
So 10 dimensions with the one time direction is fine, because 9 minus 1 is 8. Because that's needed in order to have Majorana Weil.
Right.
However, sorry, but there's a problem.
Yeah.
However, as you go up, then you have more than 32 spinors. That you cannot do.
So but in 12 dimensions you don't have more than 32?
No. Majorana Weil is of SO 2,10.
I see.
Majorana Weil of 2,10, which is the Lorentz, would be the Lorentz group there, is precisely 32 component spinor. So there is no problem. You have the right number of supersymmetries. More than 32 conserved supercharges is a problem.
That's a problem.
It's a problem because you know that would imply that you have to add higher spin fields, but you cannot have a consistent theory with a finite number of higher spin fields. I mean, infinitely many. That's, I think, the statement. So going to 13 dimensions.
Oh, you mean you cannot just add the spin 4? You'd have to add all the.
You have to add the whole
spin
thing. You have to add the whole thing. As in when you work out the effective theory, low energy theory of superstring theory, you get a lot. I mean, you have infinitely many higher spin fields in the string spectrum. But in supergravity truncation, they are always truncated out. Okay. Any questions about this preliminary part? If you have problems in working out the exercises, just tell me and we can go together. Okay? Now, let's continue on the blackboard.
Well, I mean, at some point we can also go for lunch, whenever you feel it's okay.
Okay. How much time do we have left for this hour?
20 minutes.
Yeah, we have about 15 minutes.
15 minutes. Okay. Let's let me just write down the main motivations behind. So the general introduction behind this our discussion about engaged and gauged supergravities. Now, what do we mean by them? So I will not use any formula now. It's just going to be. Can I? Okay. It's just going to be a general introduction. Okay. So this was a preliminary part to set the conventions and a few definitions, and to introduce supergravity in general. Okay.
Just maybe
Yes.
quite general question. You said in 11 dimensions there's a unique supergravity theory.
Yeah.
Are you referring to? So does this mean that you said n equals 32 supercharges is fixed, whereas in other dimensions one has a range of possible numbers of supercharges? Is that the?
That's in 11 dimensions you have just one spinor, spinorial representation of the Lorentz group, which is SO 1,10, and that is the 32-dimensional one. It is not chiral, of course, because you are in all dimensions. It's not Majorana. It's just it's Majorana, but it's not a vial. Okay, it cannot be vial. And it has 32 dimensions. It's unique. So you have just one possible choice of the gravitino field, possible definition of the gravitino field, and that fixes the whole supergravity. In 10 dimensions, for instance, in type 2 supergravities, no, there you have the possibilities of having. They have two spinners, two Majorana vial spinners, but you have the possibilities of having them of the same chirality. Then you have type 2b theory, or of different chirality. Okay, so you have a non-chiral theory, and that's type 2a theory. So you have two maximal supergravities there. But in 11 dimensions, you don't have this choice. Okay, you just have one Majorana spinner which has 32 components, and that's it. So that fixes the whole supergravity. Okay.
I mean, maybe for those who are not too familiar with spinors, I mean, maybe it's worth repeating that the dimension of a spinor representation increases with the number of dimensions. So, and it increases differently to a vector, because a vector, 5 dimensions has 5 components, 6 dimensions has 6. It goes linearly, but a spinor goes like 2 to the what is
G over 2.
T over 2.
Yeah, the integer part of T over 2.
Yeah. So
then you have to impose reality conditions where they exist or vial conditions, like chirality conditions.
And because you want supersymmetry, so you want there to be the same number of bosonic and fermionic degrees of freedom, then that constrains your the number of dimensions that you can possibly have. Supersymmetry or supergravity, let's say. because the scaling goes different. D and to do the D minus 2 over 2, so how do you match these?
That's right.
And you can do that up to 11 or up to 12 with some tricks. You can make it match. But after that, there's no way, because there's too many spinor components and too few vector components or boson.
Yeah. Yes. So this is the, and once you fix your gravitational field, which is fixed by the representation that you choose, then the rest is somehow all the rest is fixed by supersymmetry. So the bosonic field content and everything else. I mean that is kind of fixed in the supergravity multiplet. Okay, so you don't have to you have a fixed amount of fields of various kinds, form field, and one form, two forms, and so on. Okay, so that is fixed. Okay, so let's start from a general picture. To motivate our interest in gauge supergravities, how they originate, okay, what they describe. So we mentioned superstring theory and M theory as microscopic theories. Though M theory we don't know what it describes as a microscopic theory. Okay, superstring theory we do. There are a number of superstring theories. Okay, now if we assume that they are quantum, well, they provide a quantum theoretical framework where to unify all the fundamental interactions, so gravity together with all the gauge interactions, then there is a problem, because superstring theories are defined in 10 dimensions, okay, by consistency, okay, and we live in 4 dimensions. So in order to derive from these microscopic theories a model for our universe, a phenomenologically viable model for our universe, somehow we need to dimensionally reduce these theories from 10 dimensions down to 4 dimensions, okay? Down to 4 dimensions. And this is done by a celebrated mechanism called Kaluza-Klein compactification. So to go from d equal 10 to d equal 4, we use the Kaluza-Klein. Mechanism. What does it consist of? Well, the original Kaluza-Klein model was a dimensional reduction from 5 pure gravity, pure Einstein gravity in 5 dimensions to 4 dimensions, okay, on a circle. And the dimensionally reduced theory contained gravity coupled to a electromagnetism, so a gauge spin 1 field, okay? And this gauge spin 1 field came from a matrix in 5 dimensions. So this Kaluza-Klein picture provided a way of unifying somehow gravity with electromagnetism by describing them as components of a higher dimensional matrix that you would dimensionally reduce. Okay. Unfortunately, as a unification scheme, it was not successful. Okay, it also produces scalars, massive scalar. So, how do we perform this dimensional reduction from 10 or even from 11 dimensions? Okay, so superstring theory or M theory. So, what we do is we realize superstring or M theory on a background space-time which has this form here, n4 times n internal. The product, in general, could be a work product of a four-dimensional non-compact space-time, which is the space-time we live in, okay, times an internal compact manifold, which we assume to be small enough, okay, which could be a circle. In the original Kaluza-Klein mechanism, it was a circle from 5 to 4, but in general, it's a compact internal. Okay. Then what do we do? What's the dimension of this? Dimension 11 minus 4, if we come from 11 dimensions, which is 7, I guess, and 10 minus 4, which is 6. Okay, these are the two possibilities. Then what do we do? Now, we are interested in the low energy description, okay, of these theories, like superstring theory and theory. So, we start from their low energy description in d equal 10 or d equal 11. That is, we start from supergravity in d equal 10 and d equal 11, okay? And we dimensionally reduce supergravity theories down to 4. This is what we do. Because somehow we integrate out all the massive string modes. So then what we do, the reduction is effected by taking a generic field in 10 or 11 dimensions, okay? Let me denote by x mu the coordinates of the four-dimensional space-time, non-compact space-time, and by y alpha the internal coordinates, the coordinates of this internal map, okay? Now, a generic field in d equal 11 or 10, okay, will be function of both coordinates because it propagates over the whole 10 or 11 dimension of space. However, space-time has this form here, so we can expand this in harmonics with respect to the compact map. So we expand this like this. Where these are fixed functions, which are eigenfunctions of the Laplace operator in the internal space. So these y are called harmonics. They are like spherical harmonics, or if you want, yeah, if you are on a different geometry, like assume they are just the Fourier expansion. This is just the Fourier expansion. These are the eigenfunctions of the Laplace-Beltrami operator in the internal element, okay? In the internal space. This lambda goes like this is lambda squared. Lambda goes like 1 over r, where r is the size of your internal manifold, okay? So you can expand in this way. And if you apply your 10 or 11 dimensional Laplace operator to phi, what you end up with is four dimensions phi n, okay, plus lambda squared n phi n times y n, okay? If you apply your Laplace operator in 10 dimensions, okay, to this field, then you have this guy. When Laplace operator acts on y, it gives you lambda squared. Now, if this is a free field in 10 dimensions, this has to be 0. If this is a massless field, if this is a massless field in 10 dimensions, okay, then this is to be 0. But if this is 0, this means that for each n, this has to be 0. That is, this phi n are massive modes. They are massive modes, you see? So the coefficients of these expansions describe massive fields in 4 dimensions. Although you start from a massless one, you see? You start from a massless field, satisfying the Klein-Gordon equation for the massless field. No. If you apply the Laplace-Beltrami operator to this guy, you end up with a tower of massive states. How many? There are infinitely many harmonics, so there are infinitely many of these states. You have a tower of an infinite tower of massive states. The masses are lambda squared, and they all go like 1 over r. The masses, they all go like 1 over r. For a simpler example, let's consider the toroidal compactification. Okay?
When you say 1 over r, I mean, you're simplifying, I mean, what the shape of the manifold is, because it could be.
Oh, of course.
There's many different scales.
Yeah. I'm simplifying it. R is since it is a compact manifold. Okay, we can define a global size, like the minimal ball containing the manifold. Since it's compact, you can define a minimal ball containing the manifold, and R is the size. So of this ball, the radius of this ball, if you want. Okay, so with any compact manifold, you can associate a size. Okay, and the order of these masses, okay, is 1 over r. Okay, that's the size you have. Simple example. Let's consider fields on a circle. And 4 times S1. You take in 5 dimensions your fields, they depend on these extra coordinates on S1. And now being an extra coordinate on X1, okay, this coordinate belongs to a interval. This is the coordinate along the affine coordinate along the circle. Okay, R is the radius of the circle. So, since it's a compact coordinate on an interval, I can always expand this. Fourier expand I n y over r. Okay, I can perform this expansion and running from minus infinity to plus infinity. You see that this is the harmonics on the internal space, because this is n squared over r squared with a minus sign. Okay, e, I, and y over r. Okay, so these are your eigenvalues. These are your eigenvalues. Okay. Here I would say, let's write the minus here. Okay. So recall that we are in the mostly minus notation. So that here you have a plus. This plus here, you have a plus and not a minus because this enters this with a minus sign because there is this mostly minus notation. Sorry about that. Okay, then you apply your 5-dimensional D'Alembertian, okay, so Laplace operator, which is often denoted by a pentagon, but it's another square, to this phi. And what you find out that this is the sum of this applied to this, okay? So this is equal to 4 times phi n. Okay? And then here you have a term in which S1, the derivatives with respect to y act on the second factor with a minus sign, so it's plus n squared over r squared minus e to the I n y over r. Okay? And now you see that you have a tower of states. You have a tower of states. Now the result of the compactification, so the effective four-dimensional theory, okay, is obtained by truncating this spectrum, which would be infinite dimensional, to the zero mode, n equals 0. This means setting to 0 the dependence on the internal coordinates. This is what you do in Kaluza-Klein. In Kaluza-Klein compactification on a torus or on a circle, you restrict to the 0 modes in the Fourier expansion, and that defines a finite subset of fields, okay, living in 4 dimensions. And this subset of fields define the theory restricted to this subset of fields is a consistent truncation. What does it mean, consistent truncation? Well, it means that any solution of this truncated theory is a solution of the higher dimension. Okay? So when compactifying on a circle, or even on an n torus, which is the n-folded product of circles, okay? So it's just the same thing, okay? Then, after expanding all the fields like this in harmonics, and fully expanding all the fields, and you set this mode to 0, so the dependence on internal coordinate to 0. You restrict to the 0 modes. And restriction to the 0 mode is defines an effective 4-dimensional theory, which is the 4-dimensional theory resulting from the dimensional reduction. And this is a consistent truncation. The theory describing these 0 modes, okay, is a consistent truncation of the higher dimensional theory, compactified. Okay? Now, if the compactification manifold is more general, it's not a torus, but is a sphere or other less trivial manifolds, then the issue of consistency of the reduction, that is the problem of restricting to a finite number of these modes, such that the resulting theory is a consistent truncation of the higher dimensional theory, is more complicated. Much more complicated. It's a complicated issue. Okay? It's a complicated issue which has to be dealt with case by case. Yes?
Why is the right side integral on y open? Y belongs from 0 to 2 pi r, right?
Y? Because y is the coordinate on the circle. This is the circle S1.
Yeah.
This is 0. Okay? So it's the affine coordinate on the circle. So you set one point of the circle to 0, you move around the circle. Okay? Y is this distance here. It's the length of the arc along the circle from any point. So start from 0, you go around, you end up to 2 pi r, which is the length of the circle.
But it's open on the other side, right?
It's open because there is an identification. So you can't, if you would close there, that would be overcounting. Because 0, y equals 0, y equals they are the same point. So you would double count the same point. Okay? But it's a closed thing. Okay? So this is the general mechanism that you would use, the general way of reducing these higher dimensional theories to 4 dimensions. Okay? We shall be mainly interested in 4-dimensional compactification. Let me end up with a scheme. Now, let me end up with a scheme which we will use for our later lecture. But it's important to, it's a general scheme that is important to bear in mind. Can I use? Yes. Okay. Okay. This is the general scheme. I switch on this slide. Okay, so we are in D equal 10 superstring theory, or D equal 11 M theory. Now, if we compactify these theories on a manifold which is on an internal manifold which is Ricci flat, no fluxes, magnetic fluxes or field strengths, okay, that you have in the supergravity description of the 10-dimensional superstring theory or M theory, okay, across cycles of this internal manifold, so nothing, just a Ricci flat manifold, like an n-torus n-fold product of circles. If you do these very basic compactifications, well, it's basic for an n-torus, but you can also consider Calabi-Yau compactification, which is not basic at all. It can be very complicated. But if you do this compactification, well, what you end up with in 4 dimensions, or d dimensions, if you want, but d equal 4, there could be also d greater than 4, in between 4 and 10, okay, is an ungauged. So you end up with an ungauged supergravity. You end up with an ungauged supergravity. What do we mean by ungauged supergravity? Ungauged supergravity means that the vector fields, which have all masses, all fields are massless. All fields are massless. The vector fields, which are massless, and they have by consistency their own gauge transformations, are not minimally coupled to any other field. So you have a gauge group, you 1 to the number of vectors associated with the vector fields, but nothing is charged with respect to this group. Nothing. All fields are neutral. So ungauged means that vector fields are not minimally coupled to any other field. Okay? Now, ungauged supergravities, which will be the subject of our first part of the lectures, they are interesting in the sense that they have an interesting mathematical structure. They have some interesting features. They've been extensively studied, especially in the 90s and the later decade. Now their solutions have been extensively studied. They have their pros and cons. The pros are that they feature a global group, G, called G. They feature a global symmetry group, G, which in some cases is quite large, okay? And this global symmetry group has a meaning, physical relevance, since it contains part of the so-called string and theory dualities. I'll spend a few words about this now, okay? So within this global symmetry group, okay, there are contains T dualities, S dualities, and in general U dualities. So all the dualities between string theory and M theories. Not all of them, but part of them, an important part. Okay. So the presence of this global symmetry group makes this their mathematical structure interesting, and these theories it makes them appealing somehow. Okay, from the mathematical point of view. Unfortunately, and these are the cons. The cons. There are no masses. So no way of spontaneously breaking supersymmetry. Now we live in a non-supersymmetric universe, as Sam was saying yesterday. We want to at least have to have a mechanism for spontaneously breaking supersymmetry. You don't want to break it manifestly in your action, but spontaneously. And you do that with masses, but there are no masses. No way. There are no scalar potential. There are several scalar fields in general. You have several scalar fields, but no scalar potential, so no dynamics. This means, among these scalar fields, this means that these theories have a lot of flat directions, massless scalars which couple to gravity. So this would imply longer length interactions which are not observed in our universe. So from a phenomenological point of view, these theories are very bad, okay? Are undesirable because they have these undesirable features. They are not predictive. Scalar fields coupled to vector fields, coupled to p-forms, but their values is not fixed by any scalar potential to some minimum. So their value, the values of these scalar fields is not selected. Okay, so the values of all these couplings is not fixed. Okay, it's not fixed at all. Nothing is fixed. So these theories are highly non-predictive. No spontaneous supersymmetry breaking, not predictive. Nevertheless, they are interesting because of this interesting mathematical structure related to the global symmetry group, which encodes string dualities. What do we mean by string dualities? Now, we expect that the unifying quantum theory, the quantum theory unifying all interactions, including gravity, to be unique. Unfortunately, the main candidates for these theories, which are superstring theory and M theory, they're not unique. There are several superstring theories. One M theory, but there are several superstring theories. So, how do we account for this multiplicity from this picture? From the point of view of a unique unifying quantum theory, microscopic quantum theory? Well, the idea of dualities came in the 90s, just precisely to account for this multiplicity. The idea behind duality is that different superstring theories realized on different backgrounds are in fact different descriptions of the same physics, of the same quantum physics, that is, of the same quantum degrees of freedom. So they look different, but at the end they are equivalent descriptions of the same thing. Okay? And so they must have the same spectrum, they must have the same interactions, and they must have the same low energy effective theory, which are supergravities. Okay? So dualities are correspondences between these equivalent descriptions. And as correspondences, they are correspondences also between their, or better, equivalences between their low energy descriptions, which are supergravities. Okay? So dualities manifest themselves as equivalences between, in particular, between the supergravity descriptions of these two dual string theories on these backgrounds. Okay? And in most cases, these dualities manifest themselves as global symmetries of the low energy descriptions. And this is why they enter this G, global symmetry group G. Not all of them, but many of them, many of these dualities, like T duality, S duality, and so-called U dualities, they are part of G. There are some dualities which are, for instance, to give you an example, T duality along an odd number of directions. Okay, that is not contained in G. That is not contained in G. For example, T duality, what does it mean? It means that type 2A compactified on a circle of radius, string coupling constant into a background with a coupling constant which is 1 over the string coupling constant. So, in which, sorry.
So, is the statement that these T dualities are also visible in supergravity? Because you wouldn't expect that, right?
No, not all of them. Not all of them.
So when you talk about these duality groups, they refer to supergravity.
When I talk about this general duality in string M theory, I'm not talking about supergravity. I'm saying that dualities manifest themselves. So the statement is that dualities manifest themselves as equivalences between the supergravity descriptions. Equivalences. Okay? Now, certain dualities are in fact not just equivalences between two different descriptions, but are in fact global significances of a single description, within a single description.
But is T-duality an example of that?
Some T-dualities are. For example, if you take T-duality, if you do T-dualities along an even number of the internal direction of a torus, so you take 10 to 8, compactify it on a 6 torus, and you perform a T-duality along an even number of directions, that is inside the global symmetry group of the lower dimensional theory. But if you perform a T-duality along an odd number of directions, like in the previous one, you go from 10 to 8 to 10 to B,
Right.
and then the two descriptions are different.
But it's still a little bit counterintuitive in the sense that I associate T-duality with winding modes, right?
Oh.
Modes and winding modes. You're confusing that supergravity.
That's right. But when you consider supergravity, you're just truncating this out. So the lower dimension supergravity is obtained by compactifying along directions, or internal directions, but then setting all the masses, so restricting to the zero modes.
Right.
Restricting to the zero mode means that zero momenta and zero winding modes. They're all zero in the lower dimensional supergravity.
Right.
So you do the Fourier expansion, and you restrict to the zero modes in the Fourier. So n equals 0.
Right.
And this restriction is always, for toroidal compactification, is always consistent. You end up with, this amounts basically to setting all the fields not to depend on the internal coordinates.
Right. But then, sorry.
Yes.
But aren't you missing the winding mode then?
You are, but you are missing also the Klein modes.
Yeah, but you still have the zero Klein, right?
You have the zero Klein mode, but that would map into the zero winding mode, right?
Yeah. Well,
Because you have this.
For a given circle size, unless the circle decompactifies, you don't have a zero. Oh, sorry, zero. It's just a zero winding. I see, of course.
Yeah. It's trivial somehow in this case.
Sorry. Yeah,
But if you had, I agree, if you had also momenta, then T-duality would Kalosakine momenta, T-duality would map them into winding modes, and winding modes are not described in supergravity.
Right. Okay.
For sure.
Okay.
So that these are something stringy
Yeah, I can see.
that they are not described there. So so this is the picture. For instance, when you go from 10 to 4 dimensions, okay, you have this characteristic group which is SO n, n. Now the T-duality group is O n, n. So n is 6. So S is the T-duality group is O 6, 6. But G contains only SO 6, 6. So you're missing all the T-dualities along an odd number of directions. But that's because this would map type 2A into type 2B description, which differ in the Ramon sector. So they are really different descriptions. They're not unified in this picture. But nevertheless, G contains all the other T-dualities. It contains S-dualities. It contains part of the U-dualities. So it contains an important part of... this is why dualities were in the 90s were tested by famous works by Sen and others, by tested using gauge supergravities. By inspection, by comparing the PPS spectra on the two sides and checking that they matched. PPS spectra means spectra of supersymmetric states whose properties are protected by supersymmetry. So against, so if you do a non-perturbative duality, their values are not expected to change. Okay, this is the idea behind dualities, and the fact that part of this duality is in G. So,
sorry, Mario, we're quite a bit over time.
Sorry.
We're quite a bit over time for lunch.
yes, let's go.
I don't know if you want to quickly say something about the gates, or we leave it.
No. Let's complete the scheme with the right column after lunch.
Oh, after lunch, there's somebody else.
Oh no, sorry. Tomorrow.
Oh, tomorrow. Thanks.